So thank you very much indeed for viewing this video. I can't tell you how excited I am to be sharing this with you. It's been quite some time to produce this video because I've got to try and fit it in between all of the various family commitments, work commitments, all of the things that dominate life. And I should say right from the start, I submit this theory to you as a non-scientist. Yes, I have a degree in physics and astronomy, but that was 35 years ago, and I've spent my working career in the commercial world. So I'm hoping that the scientific community will look at this theory and be kind. Attached to this video, in the notes at the bottom, you will see a link to the full text version of this theory, which contains all of the mathematical derivations, and it also contains an Excel model with data provided by NASA on 5,700 exoplanets, and I've extracted 430 of those exoplanets. It's basically all of the exoplanets that are in systems where there are 4 or more known exoplanets, and I'll explain in a moment why that's important. My hope is that the publication of this theory could be one of the most important theories that's been published for many, many years. I've written it in a way that I hope non-scientists will be able to read and enjoy this theory. There's a bit of maths in there, but it's not tremendously advanced maths. It's probably, in today's world, A-level maths, I suppose. Hopefully not too many mistakes in there. But for a non-scientist to read this, my hope is that you'll be able to understand it fully. And if you are a non-scientist and you are reading this theory and you have any questions, please put them in the comments and I'll do my best to answer them. My hope is that this theory will be step 1 in a 2-step process. So the first step is to publish this theory and to get it out there. And I'd like to go through what's called a peer review process where proper scientists will look at this. I suspect I might struggle with a peer review process because I'm not really a scientist and I'm not sure they would see me as their peer. But for a theory to be accepted, it really needs to be accepted by the scientific community. So I'm hoping that the scientific community will look at this, be a bit kind about the fact that my maths is a bit clumsy or my descriptions are not really very sciencey. But my hope is that the scientific community will look at the theory and say, yeah, it's right. In terms of that question, is it right? I'm able to feel confident that it is likely to be right because there are so many things that this theory either predicts or explains that can't really be explained by other routes, and particularly the predictions that this theory comes up with. If the theory is wrong, blimey, there's some big coincidences. So step 1 is to publish the theory, get it peer reviewed, hopefully get it accepted as a new part of science. And then step 2 is the most important step, is to use this theory to convince possibly SpaceX, possibly NASA, European Space Agency, Blue Origin, some big funding agency, to launch probes to the 20 to 30 nearby stars. I've designed a probe launching mechanism that we can use to get to those stars within my own lifetime. They're quite a long way away. In terms of the launching mechanism I've designed, for the probe to get near enough to a nearby star to get the data that I want to see, and for that data then to come back to us, I'm estimating about 20 to 25 years. I'm about coming up on 60, so I'll be in my mid-80s when it comes back. So hopefully within my lifetime, but quite some time in the future. And my hope is that when you look at that, when we all collectively look back at what was the starting gun, what was the thing that made us start spreading our wings to do interstellar travel, my hope is that it's this theory. So why do I think this is the most important theory for quite some time? And it's not because it's the first new mechanical theory in science for 50, 60 years, which it is, by the way. And nor is it because it's the first orbital mechanics theory since really the works of Kepler in the 17th century, but mostly because it's the starting gun that I hope will be fired to start interstellar travel. One of my friends said to me, look, okay, and she's not a scientific person. She said, well, you've produced this new theory, you've gone on about it quite a bit. Why should I care about it? And the answer is, I hope that this theory will show to us, it will prove to us, both mathematically and using observational data, that every star out there has a planetary system. Gives us a mechanism, by the way, to understand how galaxies will also form, black holes will also form. It gives us quite a lot more of other stuff, but it will show that every star has a planetary system, and that we can calculate the parameters of those planetary systems mathematically using data we can observe already. And so what that means is, if we're looking for a planet that will support life, not just general life, but us, so it'll need to have the right distance from the star to have the right brightness, and the mass of the planet to be such that we don't either bounce around on it or get crushed. And we'll also need there to be the right amount of oxygen so that everything isn't on fire all the time if there's too much oxygen, or we aren't able to breathe enough if there's not enough oxygen. So we need to look for, I hope we will find, Earth 2.0. Currently, I don't have a design for how to get us to a nearby star. But one thing's for certain, once we design a mechanism to get probes to nearby stars, I think that it will follow that we will then be able to get ourselves at some point in the future. Because there's one thing we definitely need to do if we want to go to nearby stars. And that is, we need to design a mechanism that will help us get there. Until we start that design process, we're never going to get there. So, if you're watching this theory, and you know anyone that's linked to, as I say, SpaceX, NASA, European Space Agency, Blue Origin, please forward a link to this video to those people. If you know a person that's a friend of a friend, forward a link to this video to them, because my hope is that this can get in front of them. I'd love to hear back from someone like Neil Tyson deGrasse, who's inspired so many people in science. I'd love to hear back from him. Or Professor Brian Cox, to hear his views on, is this theory, is it right? Hope it is. Or is it wrong? Or are there these things to think about? Also, as I say, if you know people that you can forward this theory to, please forward it to them and invite them to engage with me, because my hope is that this is a theory, even in the few months since I came up with this theory, I've found so many things I wasn't expecting to discover. When your mathematical proof shows you A, B, and C, you can then suddenly extrapolate D, E, F, and G. And these are things that we can often observe. So I first started publishing this theory actually some time ago, back in November of last year, November 2023. And I published a summary video, not unlike this one I'm publishing now. And I had planned, I published it on a Sunday, and I'm recording this on a Sunday as well, by the way. I had planned to publish this on the Sunday, and then the following weekend to do a more detailed video explaining the steps behind the mathematics, etc. And in my summary, I was hoping that some kindly group of scientists would give me access to some data showing me about exoplanets. Of course, I can go onto Wikipedia and I can find the information, but you don't know how accurate it is. And I was hoping for a scientific group to give me some proper data that I could plug into my model to see if it's correct. Amazingly, I don't know whether it was by coincidence, but during that week, maybe it's the algorithms within YouTube. I posted my video on the YouTube on the Sunday. During the week, it served me up a whole load of videos with links to NASA's Exoplanet Archive. So rather than getting 5 or 10 planetary systems that I could examine, suddenly I've got 5,800. So my first thought was, crikey, my theory, I've just published it and it might be completely wrong, and I'll find out the minute I plug in this data. So with trembling hands, I downloaded the first 10 exoplanet systems. Actually, the first system I downloaded was the TRAPPIST-1 system. I really couldn't have picked a better example. because I'll explain in a moment what this theory predicts. But there are two main things that the theory predicts about any star. Firstly, that they'll all have planets and what their masses will be. And the second thing it predicts is where we will find them. So I downloaded the data from the TRAPPIST-1 system, and I looked, and there are mass estimates for the planets in there. I looked at next to my forecast model. My socks were nearly knocked completely off. It was spot on. And I thought, wow, okay, I'm a bit less frightened now. So I then looked at the planetary orbits, and the planetary orbits were where my system predicted they would be to within 1%. So I then downloaded the remaining 92, 93 exoplanetary systems that had 4 or more exoplanets in them. And I started plugging the numbers in. I hit pause on publishing my theory because I wanted to check all of these things, and I started finding out all sorts of useful extra things that I had as a hunch looking at our own solar system became suddenly backed up by data. And so all of these 93 systems are the position of the planets is as predicted by my model to within 5% accuracy, and actually most of them are predicted to within 1% accuracy. And there are a whole host of other things about those systems that this model forecasts. So I'm thinking to myself, look, I'm onto something here, and I got really quite excited about it, and so I wanted to make sure that it's right. And the more I looked into my mathematical formulae, the more I kept on discovering new things. And so in the, how long is it now, 8-9 months since I started publishing this theory, I keep on finding a new thing. And I've decided I've got to get it published so that others can have a look at this. And hopefully, as I say, NASA, SpaceX, European Space Agency, whoever, I'm hoping that we can then do start stage 2, which is to build my launching device to explore these nearby stars. So let's talk quickly. And this is just a summary video. I'm going to do another video, next weekend. I'm planning to do another video next weekend to show the maths derivations behind these. But let's just talk briefly about what's included in this theory. So the theory consists of 3 rules, 3 laws of planetary motion. The first rule says that all stars will have planets. There's a mathematical proof that explains why they all have planets, not just most of them, all stars. And when I say stars, I mean single stars, stars that are not in a binary system. Once you get into a binary system or a trinary system, you have other forces at play. But all single stars will have a planetary system. If you observe a star that doesn't have planets, then something will have removed those planets. The second rule governs how planets form within a planetary system. And the planets will form on stable orbits that are very stable. In fact, even if something moves those planets off those orbits, they will migrate back to their stable equilibrium position. And the planets will form initially in a ring of little tiny planets called planetesimals, and each planetesimal will oscillate backward and forward between its neighbours, and the smallest of those planetesimals will collide and merge with their neighbours, always the smallest first. And as they collide, you go from, let's say, 200 planetesimals in one orbit to 100, and then down to 50, and then down to 10, 9, 8, 7, 6, down to a final pair. And there's a proof in the theory that shows why those final pairs will be fairly similar in size to each other. And when they collide, their collision will shape the solar system. And then the third rule, the third law within my theory, shows that when planets are above a certain mass and a certain density, they will destroy themselves. And it's quite exciting. I think to me, it's quite an exciting part of the theory, because when I came up with this theory, the only evidence I had for it was our own solar system. So a sample size of 1. It's not really great to have a sample size of 1 if you're testing a theory. But when those wonderful people at NASA, and by the way, can I just take a moment to thank the people at NASA? How great is it that they share their Exoplanet archive for free to everyone? And that's humanity at its best, in my view, by the way. Anyway, looking at the data in the NASA Exoplanet Archive, my hunch, my thought, and as I say, the mathematical derivation of it as to why there would have been a particularly large planet in our solar system that destroyed itself is then demonstrated in system after system in the Exoplanet Archive. Now, I believe, and this theory will show, that there was a fifth planet in our solar system between Mars, or what's now Mars, and Jupiter. And that I'm naming that planet after myself, planet Peter. And the planet Peter, I've been able to calculate, will have had a mass of about 2.5 times the mass of Jupiter. Its location would be spot on in the middle of what we now see as the asteroid belt. But the density of planet Peter will have been about 9.5 grams per cubic centimetre. So not far off double the density of the Earth. It's a very dense, very massive planet would have been formed. And the radius of the planet was about 8.5 times the radius of the Earth. So physically big, very massive. And at its core, it would have contained lots of heavy elements like thorium, uranium, stuff that will give rise to fission. And if you have a final pair collision from rule 2, bringing this planet together, if you can have enough heat and temperature to start a nuclear explosion like you have in the center of a star, but the mass of this planet isn't enough to contain those explosion products, the planet will blow itself apart. And that's what I think happened to planet Peter. And it happened between 3.1 and 3.8 billion years ago. Why do I say that? Well, in our solar system, at that point, something happened. It's called the late heavy bombardment. Something belted out loads and loads of heavy material that, if you look at the moon, the surface of the moon, the big craters, they came from the late heavy bombardment. Around Jupiter and around Mars, you see groups of asteroids called the Greeks and the Trojans and the Hildas. Now, this is heavy material that came from somewhere, and they say it came from the late heavy bombardment. I think it came from the explosion of the planet Peter, and within this theory, I've calculated by 2 different and unconnected methods what the mass of planet Peter would have been. So looking at the NASA exoplanet data, I've worked out that the mass of planet Peter will be about 3 times the mass of Jupiter, but with big error bars. So 3 times the mass of Jupiter, plus or minus 1.4 times the mass of Jupiter. So it's a big range. I've then calculated from the method of calculating the mass in our solar system, I've then calculated what mass the planet Peter must have had for Jupiter to have the mass that it has, and for Saturn to have the mass that it has. And I've come up with a calculation of about 2.5 times the mass of Jupiter. So there was definitely a planet there. All we see now is the asteroid belt. And I then calculated, well, where is the rest of the planet Peter? If it's had this massive explosion, where are the rest of it gone? Well, the late heavy bombardment will take quite a lot of that mass, but most of it, and I've used computer modeling to predict this or to work out where it would have gone, it won't have had enough energy to escape the mass of the sun. Most of it would have been blown beyond the current planetary disk and would have effectively settled on its own disk, and it's what we now see as the Kuiper belt. Or, as I'll explain in the theory, the Edgeworth Kuiper belt. And so I'm making a load of quite bold statements here. It's important planetary theory, it does all of these things, we should launch probes. I should also talk about the mathematics in this theory, because there's two equations that I've been able to derive in here. The first is the mass equation, which I'm hoping, if I've been able to edit this theory, it's going to appear either over there or up here. I'm hoping you'll be seeing it on the screen. If you're not seeing it on the screen, it's because I've tried to edit this video and it's not succeeded. We'll see. So the mass equation calculates what would be the mass of each individual planet that will form around a star prior to the ignition of the sun, of the star at the center. Because when the star ignites, that will fundamentally alter the solar system, or the system around any star. What this theory goes on to explain is the physics behind how stars ignite, because what they don't do, and I remember this really annoying me when I was at university, stellar structure courses that you do, what the star definitely won't do is be sitting there nearly on, nearly shining, and then suddenly it's shining. That is not going to happen. What will happen is the star will get enough energy to form a nuclear explosion, then it will blow lots of its material out, and as it does, its temperature and pressure will drop, stopping new fusion reactions at the center of the star. But that material won't be able to escape the gravitational pull of the center, so it'll go out to a certain level, and it will then start to collapse again. And as it collapses again for the second time, it leaves behind it a nebula of gas, just like the nebula of gas that formed the planets in the first place. And it comes back to the center and then explodes again a second time. The second explosion happening more quickly than the first because the material is already heated up. And it collapses again with a third nebula left behind it, collapses again, faster and faster until the star is exploding in steady state, where the end of one explosion coincides with the start of the next explosion. And that's when you see the star in steady state. Each successive explosion will leave its mark on the planetary disk, because the exploded material, when it collapses back, part of that material will follow my mass equation and will follow I'm referring to it as Brabenian mechanics. I will follow the Brabenian mechanics, and a certain small percentage, governed by the disk coefficients that I lay out in the theory, so that the planets at the level of that explosion will be larger. And by looking at how much larger they will be, we can count how many explosions the star will have had before it reached steady state. We can then calculate back to work out, if Jupiter has the mass that it has, what mass must have been in the rest of the solar system. And that shows there's a load of missing mass. And that backs up my theorized plan of Peter. The second equation, which I'm hoping is also now showing on the screen there, shows you using, so for the mass equation, I've used classical thermodynamics to explain how material will be accelerated by the star to form planets. For the position of those planets, I've used, again, just Newtonian mechanics to look at the momentum of material as it's orbiting around the star. Where does it form those stable planets? And this is where I think I am the most confident about this theory, because there's so much data in the NASA Exoplanet Archive. And if you're viewing this video and you haven't seen the NASA Exoplanet Archive, it's a wonderful example of scientific information being shared. You can download as much or as little information as you like. You can search for exactly what you're looking for. All of the data that I've found on the NASA Exoplanet Archive confirms the position equation that I'm hoping is showing here. And so what this theory does, it explains that all stars that form will have planets. And we can extrapolate this, by the way, to cover things like black holes, galaxies. We'd need to overlay relativity, and this theory does not do that as yet. The other thing that this theory also does, it explains how we can tell from the exoplanets that we've observed whether we have yet seen all of them. And it's quite a nice little checking mechanism, because within this theory, if you download the text, and I don't know if I mentioned earlier, within the comments, there are two links. The first link is to a Word document. Hopefully it's an encrypted Word document, but it's a Word document you can download and you can read, and that has the full theory of the full text of the theory and the mathematical derivation. And as I mentioned before, I've tried to write it for a non-scientist to understand. The second document is an Excel document, and that has details of 430 exoplanets linked to 93 systems, and I've color-coded them, and you'll see in the Word document the explanation of the color coding, so you can see how accurate or inaccurate each of the forecasts is for the position of those stars. Just by looking at the position of the planets, rather, around those stars, we can predict whether we've seen all of those planets. And within the text theory, I've made a number of positions as to where we will find more exoplanets. And in fact, actually, even last weekend, when I was finishing off the text version, I found a few new exoplanets have been discovered, and they're where I said they would be. So I'm quite excited about that. I'll also go on to explain in this theory why Mercury is the innermost planet in our system, and I'll explain that mathematically. So that really is the smoking gun that says this theory might have its flaws, but it's not wrong. I'll explain why Venus is rotating the wrong way, opposite direction to all the other planets, which is again quite nice. Earth was formed from the collision of a planet Theia and what eventually became the Earth. Where on earth did Theia come from? This theory explains precisely where Theia came from. Mars in our solar system is quite a puzzle because it's smaller than the trend you would expect between Mercury, Venus, Earth. You'd expect Mars to be larger. You'd also expect Mars to be more dense. And in the theory, I will explain why I think that Mars, the main planet that would have formed Mars, will have been subsumed by its larger neighbour. And the time it will have been subsumed will be during the final pair collision that will have formed the Mars system. The larger neighbour to Mars is, we don't see it today, it's what's our asteroid belt. And I am theorising in this theory that there was a planet, I'm calling it Planet Peter, between Mars and Jupiter, and it was enormous. So if you add up all of our planets in the solar system today, you will find that Jupiter accounts for 2/3 of all of that mass. The planet Peter would have been, I believe, about 2.5 times the mass of Jupiter. So it would have absolutely been the largest planet, and it would have blown itself to pieces, leaving just what we see now, which is the asteroid belt. So there's a bit of a spoiler alert in there. Then you have Jupiter. Why is it so massive? This theory explains exactly why it is so massive. And Saturn is another puzzle. There's two things about Saturn, and they're two really big things that are a puzzle. The first is, if you look at Jupiter, Uranus, and Neptune, the four outer massive planets, they're all about, sorry, three of the four massive planets, they're all about the same density. Saturn is about half the density. Why? And why is the gaseous makeup of Jupiter as it is? Well, this theory explains that because of the way the star forms, the planet outside of what I refer to as the tide marks, so the distance that these explosions go to of the material that's in these explosions, that will leave a mark on the planetary disk where the most massive planets will form. Just outside that tide mark will be the lighter fractions of gas. And so you would expect wherever there's a tide mark, the next planet out will have a much lower density, which is exactly what we see with Saturn. And then we see Saturn's ring. Saturn's famous for having a ring system. Now, when all of the material in the rings around the star were forming into planets, why did Saturn's ring system not resolve itself into little moons? And the answer is because there's no frictional gas in there, because Saturn's ring system will have come from the collision of material given out during the late heavy bombardment when planet Peter destroyed itself. Moving on through the solar system, you then have the planet Uranus. Now, Uranus, talking about Uranus, that's never going to be not funny. But Uranus is rotating at right angles to the rest of the planets in the planetary disk. Why is that? And again, I believe that's because of the late heavy bombardment, and I've done some computer modeling to check this, and that does appear to be the case. Then you have Neptune the Mystic, as Holst described Neptune in the Planet Suite, the outermost planet in our solar system. And Neptune's orbit is a puzzle because it's a little bit nearer to the star than it ought to be. And this theory explains precisely why that is. And it uses that as a marker. And when I first was starting to publish this theory in November of last year, I thought this was a bit of a fudge. But what I found is that in about 20 exoplanet systems, exactly the same nearness to the star is observed in the outermost planet. And I've suddenly realized why that is, and this theory will explain exactly why that is. And then the last thing, looking at our own solar system, is there a planet 9 outside of Neptune, further from the star from Neptune? And a lot of people have looked at the movement of material in the Kuiper belt, or the Edgeworth Kuiper belt, and they've theorized there must be a large body out there, and it might be the 9th planet. My theory says it is not, and that Neptune is the outermost planet because it has the mathematical marker of being the outermost planet. If there is another body outside that is very massive like a planet, it will have come to our system via some other route, because the mathematics that shows why our planets have the mass that they have dictate that Neptune must be the outermost planet. So just to summarize all of this, I want to be clear. I am not a scientist. I am an amateur scientist, or a hobby scientist. I'm very excited about this theory, but I'm not a scientist. And so I'm presenting this theory to the scientific community in the hope that, well, on the one hand, they'll be kind in their analysis, but on the other hand, that they will apply proper scientific rigor to this. Because I think, even in the short period of time that I've been looking at my equations, I've found lots of interesting things like retrograde planets. I mean, that is fantastic. My theory predicted them, and my first thought was, oh no, that's a mistake, because you're not going to have a star rotating this way and a planet rotating in the opposite direction. And every which way I looked at it, you have to. Blow me down when I saw the NASA Exoplanet Archive. Suddenly you've got retrograde planets with no explanation other than the cosine mechanism, which is clearly not what's caused it. So just to summarize, we've got, hopefully if you go to the bottom, there should be 2 links. Put in if you can't download those documents to review, the Word document and the Excel document, if you can't download them, please put a note in the comments so that I can find out what's wrong and make them so they can be downloaded. I'd like to put a few thank yous in here as well. When I was at university in 1989, well, finished in 1989, my astronomy professor, Professor Leon Mestel, he was a fabulous guy. In fact, I would have done a PhD and possibly would have stayed in science had it not been he was retiring, and he was marvellous. I'd also like to thank my physics teacher from secondary school, Mr. Woolley. Mr. Woolley was, again, an inspirational man. He still is, I think. I don't think he's died. Former Professor Mestel is no longer with us. I think Mr. Woolley is still there. Next weekend, I'm going to hopefully download another video that will give you the mathematical derivations, because not everyone's going to want to read my text document. The text document is 168 pages long, so it's quite long, because most scientific theories will explain a tiny little bit, or a new step slightly forwards, whereas this theory is explaining a whole wide area. So I've tried to keep it not too long, but it's not as short as I'd like it to be. And then finally, before I close this video, I'd like to say that I do think this is an important scientific video, and I do think that this will help our understanding of the cosmos a lot better. But the main reason why I'm excited about this theory is, and I'm hoping that viewers of this video will help me by forwarding this theory to those people involved with SpaceX, NASA, European Space Agency, Blue Origin, with a view to them backing this proposal for me to launch, or to use this design to launch probes to nearby stars. Thank you for watching the video. I hope you've enjoyed it, and that's it. Bye for now.